Well, it's my pleasure to kick off today's faculty interview and to present our very own Hali. So Hao is a postdoctoral scholar, a postdoctoral fellow actually, here at Princeton. He received his PhD at ETH Zurich, and he won the Swiss National Foundation's fellowship for young scholars while he was there, and that enables his postdoctoral studies at Princeton and Columbia. Hao works in the area of geometry, and in particular geometry capture. He's done amazing things in this area, and those things have had a lot of impact already. They started having impact back when he was a PhD student. His work is already found in technology pipelines of Lucasfilm, Industrial Light and Magic, and various other studios. They constantly bring him in to get his secrets. He's collaborating with medical researchers on applying that work to radiation therapy, where geometry needs to be tracked. And Hao is in very high demand. He's done extended visits to the University of Singapore as a visiting scholar at Stanford and at various other institutions in academia as well as in industry. So without taking any more of Hao's time, it's my pleasure to introduce to you Hali.
Thank you so much. Very pleased, distinctly honored to be here. So I'm really excited to show you some of my latest research on performance capture. It's very, very cool and very hot topic nowadays. The title is called Geometric Capture of Human Performances. So performance capture has been applied in the traditional side of computer graphics in various fields to bring digital characters to life. Right? Here's an example from Avatar. And the idea is that you put markers on a real person's human body and try to track where these positions are going. So you can do exactly the same thing for the face. Here they're wearing a head cam. And you try to map these motions onto a digital character so that you don't need an artist to keyframe every little things, every little motions to create the animation. The downside of using markers is, besides you need to wear all these things, not very comfortable, you're not capturing all the information. For non-human subjects, that's okay, because we need to interpret how these alien characters move, right? So, but if you're interested in having a realistic human performance capture, here's one example from the curious case of Benjamin Button, which in my opinion is so far the technologically most advanced results that people have created in cloning a digital human that looks absolutely real. So it's indistinguishable from reality. So the idea here is to map the face of younger Brad Pitt onto an older version of Brad Pitt by looking at a reference image. So this technique involved a lot of computer vision techniques, but what you needed for this to make this happen is you needed artists in the pipeline, in the production pipeline. So what you might not know is that it requires 3 weeks for only 10 seconds of animation. So it took 2 years for them to recreate the entire film, which the head is completely CG, computer generated. 3 weeks for 10 seconds. My goal is to make this automatic, no artist in the loop, and in real time as much as we can. So since the beginning of my PhD, I've been looking at different things. Here's one example of where I was looking at what is the right sensor to capture information so that we can actually make these things automatic. So here's one of the systems that we were using that was exploring. It's a real-time 3D structural light system. The idea is very simple. You're projecting a pattern, so in that case it's based on phase shift pattern. And you have 2 cameras that solve stereo, and you get this in real time. So we get a depth map that is being captured at 30 frames per second. What I want you to see is that if you look at the geometry that's being captured from the subject, you can tell what the person is actually doing, but simply looking at what the geometry is. There's no texture, nothing, not a video, but just looking at the geometry, we're able to do that. The premise here is the following. It means that we're able to capture motion, potentially capture motion, at the same resolution as geometry, in real time. So This is great. I mean, you've seen those prototype systems that can capture a small volume, but we're also interested in capturing the entire full body, right? We want to duplicate an entire person. So here's one collaboration that I was working on with USC ICT, with Paul Debevec. They built a huge, gigantic dome, used photometric stereo, and a surround camera, so basically 8 cameras that are put around the subject and use photometric stereo to compute these highly detailed geometry. One thing you'll notice right away is there are a lot of holes in it, right? So it's incomplete. So this is one of the limitations whenever you're trying to do optical acquisition. You won't be able to capture the entire thing. But still, we're very interested. If you, as a human, we can recognize what the person is doing. So the question now is, what is the research goal? The goal is, what can we actually do with this type of data? What can we do with depth acquisition, geometry acquisition? So my research goals go into 2 main directions. The first one is slightly more on the traditional side of computer graphics, which is, if we're given this, how can we obtain a full body reconstruction? Every hole is filled. This, by the way, is the latest result that we're going to present at SIGGRAPH this year. How can we obtain a full digitization of that subject? So this involves a low-level reconstruction, dynamic shape reconstruction. The first thing is geometry, more complete geometry, frame-to-frame correspondences, so that we're able to extract information such as kinematics, or maybe we want to go a little bit further and explore dynamics, physical materials. So this is one direction. The other direction is more on a high-level side, computer vision or recognition type of problem. So what is the current gesture? What is the current body pose? If we're looking at faces, what kind of facial expression is the person currently doing? Or we can go further and look at what are the emotions, what are the intentions of that person. So these things are very interesting. What I'm going to show in this talk is specific on the face, that these 2 components are actually coupled. They work hand in hand. So what it means is that simply if I have some form of high-level representation, a high-level prior, I can improve the reliability of the reconstruction in the low-level domain. If I have a richer low-level reconstruction, I automatically get much more semantics out of it. So all this is like great and good, but the question is, are we only limited to studio setups in laboratories? So one thing I believe that this is going to impact computer graphics and beyond computer graphics is for one reason. It's because of this. So we have one system right here, which I'm going to do a demonstration later. It's a low-cost 3D scanner. So the way sensors are going to change, and we'll have the chance to massively collect tons of data and also like exploit these kind of technologies on a very wide range. So let me start with what is dynamic shape reconstruction. So you've seen before the low-level reconstruction side of things. So the goal is the following. Here's one example that we have created using the previous structured light scanner, the first structured light scanner I've been showing. The goal is the following. I have a single view input of a dense reconstruction. The first problem is, how can we obtain a complete digitization of the hand having the same motions from frame to frame? So the way it works is, so here's the naive way of doing this, is a template-based approach. You have a sequence of frames of the hand scan, so scan 1, scan 2, scan 3. We analyze the deformation, and let's say we use an artist in between, he creates a model, or I'm using a static reconstruction approach. These things are very mature technologies, to create a hand, and I simply apply the deformation onto that hand. Right? So you get a deformed hand, full model of the deformed hand in the second pose, and you repeat this again and again, and you get the third one. Sounds very simple, but it's not. It's actually not. So the problem is, how do we get the deformation? How do we analyze the deformation between consecutive frames? So the problem is the following. If I have a sequence of hands, how do I actually know that this tip of the finger is matching here? We as humans, we recognize that. But it's hard to tell the computer that this is simple. And the reason is because we're not carrying markers on our hands. And the second thing you can see is incomplete. So there's a lot of occlusions, and there's no frame-to-frame correspondences happening. So let me show you how that works on two frames. So the problem is a correspondence problem. We want to establish dense correspondences between these two shapes. And the way I'm going to solve this is using an approach called non-rigid registration. Non-rigid registration has been around in computer vision, computer graphics for a while. But I'm going to show you a particular version of it, very, very robust implementation, and why it works, and explain you why it works. So here's the problem. I have a source, I have a target. That's a scan of me using the same scanner in this pose, and then I'm lifting my head, and obviously there is some deformation happening and also some global pose changes. So I have no idea where the correspondences are. Also, I have no idea where correspondences exist, right? I mean, both are part of each other. So here are the overlapping regions, the missing data, and what non-rigid registration is going to give me is the following. It's going to automatically bring the source onto the target without using explicit search for shape descriptors. So I'm going to show you a refinement method that is only based on local proximity heuristics and basically warps, it's an optimization technique that warps the source toward the target automatically. So the recipe is the following. You have a source, you have your target, and the first thing we need to solve is what are the overlapping regions? We have solved that. And within those overlapping regions, I want to know where every shape is, where every point, the point-to-point correspondences are matching. And once I have those, I can say, how am I going to deform the source toward the target? Sounds very simple. The problem, however, is the following. So let's say I'm given the two shapes, source and target. First of all, it's deforming. So if I'm only looking at the local geometries, it's going to change. So it's very hard to say that this part is also matching here. The second problem is ambiguity. So that obviously doesn't have much of a shape in it. It's just simply like a very flat plane. But it could also have been matched to this part. So how would I know that? Last set of problem is the target is incomplete. So if I have that geometry here, so it's basically a face, right? How would I know how the mouth deforms here if I only have partial correspondences? So I need to introduce some form of geometric priors into this deformation model. So we're going to make the following observation, how we're going to solve that problem. So we have this dependency here, overlapping region, correspondence, deformation. The observation here is the following. If I have some form of deformation that is very close to the target, it's easier to solve what the correspondences are because the correspondences should lie in the near proximity of it, right? If I have that, it's also easier to find where the proximities, where the overlapping regions are. So you have this like two-way coupling in that setup. So why not just solve everything at once? Solve a global optimization using a local refinement method. Everything is very nonlinear, so we need a good initialization for it too. So let's take these three components and throw it into a global solver. And let me show you how that works more specifically. So we have our source, we have our target, looking at every vertex. How can we initialize the correspondences? Well, we need some form of initialization that depends on the previous position. So let's just take the simplest case of saying we're doing shape matching, of course. So let's take the closest point. So we take every vertex and map to the closest point to the target. And we replace the closest point, the correspondence stage, with the closest point. Now, instead of doing overlapping regions explicitly, because we don't know where they are, we simply say, as a simple heuristic, so we're going to define three heuristics. First one is, I'm going to remove those that are too far away. In the end, when everything converges, it's not going to map onto the boundaries. So I can remove those two, and I can also remove those that have incompatible surface normals, right? So if I have all these things, I can replace pruning. This is not part of the computation. It's simply an initialization to the optimization. But as I said before, I was looking for the deformation. But the global optimization will involve a coupled optimization between correspondence and how everything deforms. So instead of deformation, I'm going to solve for a global optimization. So because there is a deformation model involved, we can do one thing with the deformation model. We can say it's very stiff or it's very soft, right? So let me start with something that's very stiff because it doesn't make the subject go into some wrong local minimas, it avoids that, and check if it converges. We check if the optimization is converging. It's not converging, I recompute everything. Once everything converges, I can say reduce the stiffness. This is like, sort of like a course-defined optimization in the energy landscape. So we converge, and we relax the stiffness, and we go again and again. So this is like the overall principle of doing this kind of optimization. So you have these two inner and outer loop that you're going again and again, and you can obtain this sort of like robust, non-rigid, iterative closest point algorithm. This is the overall idea. The question is, what is this global optimization? So as I said before, we're looking for a deformation model. So what the type of deformation model we need here is it has to preserve details. It should avoid scale, distortion, shearing. So we're going to say we also need something that needs a local support. We want the energy to be distributed evenly over the entire shape. So what we are looking for is something that looks like this, a very natural deformation, something that's very elastic between two frames. Another thing that we can do to that is to avoid local minimas in a multi-resolution framework. So we can decouple the complexity of geometry from the deformation. So instead of solving for every vertices, so not only is this more robust, but it also gives you, it's much more efficient. So instead of solving for every vertex, we're going to have an intermediate representation of using a deformation graph. You can also use adaptive deformation graphs. It also works very well. So here's just a simple example of using a uniform graph. And what we need to do is to solve for the node positions. And these node positions should define, as you've seen before, detail preservation and global consistency. And these are satisfied using an energy term that maximizes local rigidity. Basically, it avoids it to shear and to distort into scale. The second one is local smoothness. There are two ways of doing that. One is you can say every node that's attached to an edge should move similarly, or you can say they spatially influence each other in the same way. So we take these two energy terms, but if you want to do some deformation, you need some energy that pulls it, right? You need to change something. So the most obvious thing we can do is we can just take the closest point. And this is not very interesting, but it's the most obvious thing we can do. What is more interesting is how do we solve for the correspondences as well. So our initial way of solving this is to equip every target correspondence with a parametrization. So we would solve not only for how this thing moves, but also solve for where the target correspondences go. So this becomes a global continuous problem. It's very complicated to solve, especially because the target has holes. So the question is, how do you fill in some parametrization in these holes? So we figured out that a much more simple way in solving this is to use something that Chen and Medioni have introduced in '92, which is a point-to-plane distance. The idea is very simple. Instead of solving for, you need to push the source toward the target, but instead of minimizing the distance between the points, you're minimizing the distance between the point and the plane. So you're allowing the target to glide on the target surface. This, in some way, is a, it's like a first-order approximation of a very dense target scan. So we use the point-to-plane distance metric and put all these four. We can also remove that, but if we use that, it's a little bit more stable because we have these discrete closest point estimations. So we put all these four energy terms together, and unfortunately this one is blue, which says, hello, I'm actually different, I'm nonlinear. So the nonlinearity can be solved using a simple Gauss-Newton method because everything is a nonlinear least squares problem. So we use Gauss-Newton to solve this, and luckily we're using a deformation graph, and every node is surrounded by a finite number of neighbors, which means that the structure is very sparse. So Gauss-Newton means is an iteration of different sparse linear systems. So all these sparse linear systems, all these linear systems are sparse. So we can use a direct solver. So one way is to use a sparse Cholesky solver. And that's it. Now we have a black box that can do robust non-rigid registration between two frames. So let's see how we're going to do that in a multi-frame setup. So we have it's the same slide as before. You have scan 1, scan 2, and take the template that is aligned with scan 1 and then apply the deformation onto that. Basically, we're warping this template toward the scan of scan 2 and obtain the deformed one. That's it. The question is, so I mean, in the first place, how do we actually get this one? How do we get the first one aligned to the first scan? Well, we do exactly the same. We're doing exactly the same non-rigid registration. And just to show you that how robust this is, I'm going to show you on a different example. This one is sort of ridiculous. So we start with an initialization of a scan that is it's not even looking toward the same direction. That's the template. It's a generic human model in a pose like this. And I have a different pose of a target scan. And this is a scan of a different person. So let me just show you if I press the button. So it's incredible how robust this is. And it's really this optimization, all these optimization ingredients that make this system so robust. If you remove one of them, it's not going to converge as good. So here's some more results if we just apply the thing on different scans. We usually use a checkerboard pattern to show that everything is not drifting around. I'm going to show you more careful evaluations later. So here's really single view capture, full reconstruction of a puppet. Here's another example. This is interesting because it can capture plasticity, right? Everything is fully based on geometry. So we're not adding some assumptions about what kind of deformation model we're using. And the last example, facial expressions. This is sort of like the holy grail in computer graphics, at least for facial animation. Capturing faces at high resolution. It can capture this. There are two problems here. What happens if I put my hand on my face? So what's going to happen is that you're going to screw up everything else because everything is like ordered. And if I have one frame that fails, everything in the back is going to fail. And that's not acceptable for an everyday usage, right? If you want to use it at home, I don't want to have a careful studio setup. Second problem is speed. I have to solve for thousands, 10,000s of nodes at the same time. Even though it's sparse, we can do all kinds of like parallelization to get it fast, but it doesn't guarantee you to have real-time performance. So we want to have this. We want to be able to use this in everyday surroundings. And another problem, if you use a Kinect like this, you get this kind of data. If we use this, you get something that's very high quality. Unexpected occlusions. A person is wearing glasses. He has a hand in front of the face. We want to be able to reconstruct the face as well. So what do we need here? First of all, we need real-time performance. We need robustness to noise. And we need to be able to extract semantics. Right? We need to say, it's not the face, it's a hand. So I'm going to explore this on faces. So yep.
Sorry to interrupt, but does your model or your constraints take advantage of the fact that different parts of an object have different degrees of articulation?
The model.
Yeah.
The model.
Does?
Yeah. So the model, if the model is very general, so you can you have a lot of degrees of freedom. If your model, say, are specific, I'm going to talk about this right now actually. If your model is very specific to faces, for example, you can say, what is my space of plausible facial expression? So I want to project everything that's wrong onto that space. Does that make sense? All right. So our first prototype of a real-time facial tracking system. It's called FaceOff, so that was awarded like Best Paper Award at SEA. And here's what's happening, right? It's me at that time doing some crazy expressions. And this is what the scanner is seeing in real time. What we were able to do here is that we were able to have a template tracked fairly accurately to what's actually happening. It's not fully accurate. I'm going to show you why in a moment. But it's in real time. That's the point here. So the way we achieve real-time performance is we need to reduce the amount of variables that we're solving for. So in order to do this, we need to add some knowledge to the system and tell it, what is a face? So that's exactly what I was saying, like for these plausible facial expressions. First of all, we use the method we've done before, non-rigid facial tracking, and do it on very short frames, let's say 100 frames, maybe 200, and arbitrary expressions. We take, for one specific person, we just say, smile, make this expression, have some conversation, and have short frames where we can reliably track everything. It doesn't matter if it drifts or not. And the good thing about faces is that, and that's why I'm actually working on faces for the first part, is because faces are very linear. So what does it mean? You take an arbitrary face, it's a linear combination of another face. So we can use simple principal component analysis to reduce the dimension of what I'm actually solving for. So I say a face is basically it's a neutral face plus the difference to that neutral face of different expressions. And if I do principal component analysis, I can take the most important eigenvectors, have them sorted. Let's just keep, like, let's say 32 expressions. That's actually what we used before. So 32 are sufficient to create arbitrary facial expressions. And what does that mean? That means that if I'm having an acquisition system, I'm capturing my face, I just need to solve for all these coefficients instead of solving for general points. So that makes it very robust. This is old, so this existed before we came up with that. The problem here is, let me just show you what the problem is. We're using PCA, so each of these expressions don't have any meanings. They're basically just low frequency to high frequency. There's no control over it. The artist has no way, and that's one reason why this was never really successful in production, because the artist has no control over the face anymore. Artists always want to have a way to tweak things. The second reason why it's not very successful is because there's no easy way to retarget that facial expression onto a different character without training that target character. And also, if you want to map that face onto a completely different character, like a cartoon character that has nothing to do with a human, a crocodile. So for that, you need some form of semantic meanings for the extraction. So what we need now is basically a way to incorporate semantic priors. To incorporate semantic priors, one way in computer animation is to use something called blend shape animation. So we have blend shape animation. It's basically exactly the same. We have an expression and linear combination, but instead of having arbitrary eigenvectors, now we have specific facial expressions. So mouth is open, you have an eye that's moving, eyelids left up and down. So you have some form of semantics happening. So if I solve for this, I get something called blending weights. It's basically just the coefficients of them. And these blending weights are a form of shape expression descriptor of what this facial expression is doing at the moment. So what you can do with that, you take this expression, take its blending weights, and can do retargeting on arbitrary cartoon characters. This is great only if I have a compatible blend shape model blend shape equation between the target and the source. Unfortunately, if you want to construct such a blend shape model, it takes a long time. And the reason for this is for some form of like natural, realistic and facial animation, you need at least 40, 60. If you're looking for really realistic things that they use in Avatar, you need thousands of blend shapes. So it means that each of these faces needs to be sculpted by an artist. And we don't want that. So if you want to avoid this,
actually,
yeah.
In some films it can go up to tens of thousands or hundreds of thousands.
Wow.
Yes.
So it makes it even more
You
useful.
spend over 2 years sculpting faces for some characters.
What a waste of time. So instead of doing 10,000s of blend shapes, let's say we just do it once. So we just spend 2 years doing 10,000 of blend shapes. And we reuse this information so that we don't need to do it again and again in the future. So an obvious way of doing this is to use, do it on a generic facial model and have one target model in neutral position and basically transfer these expressions to it. Oops, sorry. so that we can get all these different expressions. This exists. There's expression cloning from Noah Neumann. Sumner Popovich developed deformation transfer. And you can do this, right? The only problem here is that if you have a generic mesh, let's say you get this kind of expression, but what the ground truth really looks like, and this is actually me, supposed to be me, is this. And the reason is because you're transferring geometric details from an existing source to the target. You'll also transfer things that didn't exist on my face. So you have all these like wrong artifacts that are being transferred there because the system didn't know how I would look like in certain expressions. So the question is, how can we make this easier to construct? How can we make it more accurate to my face? So we need to provide some form of training to it. And this is what we came up with. This is called example-based facial rigging. That was shown at SIGGRAPH last year. Actually, it's almost 2 years ago. It's basically a black box. And we have exactly the same thing. We have one neutral face of the target. This is what we want to obtain. What are the blend shapes here? So this is what we want to obtain. We want to obtain the target blend shapes. And we have, this is what we would have gotten using simple deformation transfer. But what we want now is that it matches certain input training poses. Training poses that are completely arbitrary, and we have no idea what their blending weights are. So we're going to solve for what are the best possible blend shape that simultaneously matches the semantics of what my prior generic model gives me, but also the linear combination of that would give me arbitrary facial expressions that given as input. At the same time, I also want to know what these expressions were. So this turns out to be a bilinear problem. So this is my linear equation. I have coefficients, which is the coefficients, the blending weights, and the blend shape that I have no idea of. And this should be equal to my input training poses. So small set of input training poses of different expressions. What I want to solve now is what are the blending weights that correspond to those, but more importantly, I want to know what are the blending shapes. So the way we're going to solve that is we're going to decouple these two things and solve them in an iterative fashion. Step A and step B. Step A fixes alphas, so we need some form of initialization of alpha. The way we do it is we first initialize everything using deformation transfer and solve for the alphas. Once I have the alphas, I obtain the blend shapes. So once I have the blend shapes, I put it into the next equation, the same equation, and fix the blend shapes and solve for the alphas. This you iterate 10 times, it always converges to something meaningful. One of the instances sounds very simple. The hard part is actually how do we actually compute these blend shapes. So there are a lot of vertices that we need to optimize for. I'm not going too much into detail on that, but I'd like to show you an important insight that we found, which is that this whole thing has to be computed in something we call the gradient domain in gradient domain. So if we solve everything in vertex domain, which means that we're solving for position of the vertices, we get something like this. So you get some weird artifacts on the face, but we delayed something that we call the Poisson solve. We're solving for a Poisson equation. Now by delaying this, we obtained this really nice shape in the end. So it has to do with some coupled regularization happening in the optimization. So I'd like to show some comparison of how meaningful this example-based facial rigging is. First of all, we have a neutral face. If we use deformation transfer, no examples, we get this. So it's basically a generalization of deformation transfer. And if I have just add in 6 examples, I get these like really fine lips of that character. And the reason for this is that because there's one input example that had fine lips. This is neat. It's very cute for artistic work, but it's very, very powerful in terms of tracking. And the reason is if you do tracking with deformation, it's never going to work. But it works if we have a little set of input training data. Instead of before with PCA where we needed 200 input trainings, we only need a very little set. We can now build a blend shape model that we can use for tracking. So this was our first real-time tracking of a face that looks, it's very realistic. So we built, we basically built a blend shape model based on fax poses. and it has 74 blend shape equations, and we only use 15 expressions to train that system. And you get this in real time. So that was our first result. So a few months later, the Kinect came out, and we're like, oh, wow, cool. Why don't we just plug the Kinect to it, and let's see what happens. And you're going to see what happens. It's flickering. It's flickering like hell. We're like, oh, God, we want to make a product out of it. How come? It's not going to sell. So, it's very noisy. It's incomplete. What's that? That thing? That's the input data. So that's what the Kinect sees. The Kinect sees the video, and the depth data looks like this. So it's very unstable because it's cheap. So what we wanted to do is to fix that and to have a more sophisticated algorithm to produce. It's not only like fixing this flickering, but it's also producing work within a space of more plausible poses. So I'm going to show you how to deal with noisy input. And we're introducing something called probabilistic animation prior. It's something based on regression analysis. So the way we're doing this is, what we want is a stable tracking, right? We have our input, VGA camera, and we have some input data, and we're basically, the output is a set of coefficients, and we're using what we've constructed using example-based facial rigging. In addition to this, we're going to build something called an animation prior, which is the space of all possible animations that could exist. And animations are basically a sequence of poses, and the sequence of poses are basically a sequence of expression descriptors that you've seen before, the blending weights. So we can just take these expression parameters, put them back, keep a history, and try to map this history onto the animation prior space. And this is what we literally did. So we took 3 artists, gave them 2 weeks before the SIGGRAPH deadline, and I took random videos from YouTube, even from myself, and asked them to replicate as close as they can these realistic animations. We took professional animators, that's their job. Right, they have to tweak, they have tons of sliders and try to tweak these parameters and try to get as close as they could. We created 9,500 frames from these input animations, made them smaller, more exaggerated, less exaggerated. And what we did is we put them as a prior. So this is how it works. So every expression is a point in an n-dimensional space. So the n-dimensional space is basically each expressions. For example, smile or mouth open. And every point, basically every blending weight is a point in that space. The observation, however, is like, why does it sometimes look so crappy? Why do we have like these weird expressions happening? And it's because it's like a linear approximation. I mean, we're linearizing everything, and it's not linear. So most of the times we get these strange artifacts in that space. And the question is, what are the right poses in that space that looks nice? So we want to include animation manifolds. Animation priors. So an animation is basically a one-dimensional manifold in that n-dimensional space. For example, a curve. So we have the sequence of expressions, and we have tons and tons and tons of them. What we want to do is that, given this noisy data, if we just solve it naively, we get some random point which might look a bit weird, a little bit off, but we want to push that point onto that animation curve, something that we say exists in real, or is plausible to exist. So this is what we call the correction. This is the goal. So one way to do this is to use some technique that has been introduced actually 3 years ago by Lau and co-workers in their poser system, face poser system, so they basically sample these curves and build a Gaussian model out of it. So it's like a probabilistic expression prior. So everything is static, and you need a continuous representation of this so that you can have an optimization where this point converges to the curve where you want it to go. The problem, however, is if you just take into account everything as static, it might actually be projected onto a different curve. So that's why you still get these flickering effect. But what you want to avoid is that you have this flickering. So the observation is the following. So we look at what the artists were generating when they were creating their curves. They're using Bezier curves, splines to do the animation. And basically it always looks pretty smooth. So in some ways what it means, we want to include temporal coherence into the solve. If we just include temporal coherence, it's going to look very stiff, not very good, but we want to match everything as close as possible to the animation prior. So to do this, we take a look at a little history of blend shape coefficient solves. The way we're going to do this is we're going to look at a window of m different blend shape expressions. So this is when we now introduce something called the temporal joint probabilistic distribution model. So the idea is we're looking at a sequence of facial expressions, and we're going to model this probability distribution function using the following model. So it's something called MPPCA model. So it's a mixture of probabilistic PCA. It's nothing else than basically a mixture of Gaussians. We're using 20 Gaussians, mixture of Gaussians, and that lie in a local subspace, so local PCA subspace. So the parameters of that models are basically, Gaussian parameters. We have weights, mean, principal components, some noise in it. And we're going to use these animation priors that we've generated from the artist, that the artists have generated, and put them into this, this model. Using expectation minimization, we can train for these parameters in latent space. And once we have that, we have a form of reduced dimension model of what is an animation prior. So the question now is, how are we going to solve for the target expression? So basically, it's a Bayesian inference problem. We can solve this using within the maximum a posteriori framework. So we have our expression. What is the current expression? How do we correct for it? It's basically what is the most likely blend shape given the current data and a sequence of previous animation sequences. So by conditional independence, we can rephrase this equation as a product of likelihood and prior. So it's standard technique. This prior is basically exactly the same as the MPPCA model you've seen before that we have trained using the animation sequences. And in addition to this, we have the likelihood model. The likelihood model is very simple. It's basically, given the current blend shape, how far is it from my data? And we're adding two different terms to it. A geometry term, which is simply point-to-plane distance, basically a Gaussian function, Gaussian version of point-to-plane distance. And the texture is optical flow. Optical flow tries to minimize the intensity change between subsequent frames. And that's basically it. So now I'd like to show you everything I've shown you before, everything we've discussed as a live demonstration. I would like to show you within a framework that we called phase shift. So it will take a little while to load. So the idea here is that I'm going to, first of all, do a facial animation tracking, and I want to do retargeting. And as you can see in everyday surrounding. So the first thing is, so now it's initialized. This is what the Kinect sees. This is the acquisition device. Okay, so this is like the depth map. Can you see? Right. And what I'm going to do now is I'm going to do example-based facial rigging. I want to build a rig of my face. It's basically an understanding of how my face can move. So here's the, I'm a little bit short. Okay, maybe I can just, okay. So I want to build a neutral face. It uses super sampling, similar to Kinect Fusion. And I just record 7 expressions. Oops. Browse up. And teeth. Right? So I've created like a few scans of my face, and I want to build the blend shape out of it. So now I'm constructing a rig. And this involves non-rigid registration, as you've seen before. And it also involves like this optimization that creates these blend shapes. So this will take a little while. You can see is going through every expression. But it's fully automatic. I'm not doing anything. It's also constructing the textures so that we can use for optical flow and for different things such as eye tracking, etc. Okay, it's almost done. Now it's constructing a texture. And that's it. Now I can use it to track my face. This will involve everything you've seen before. So tracking. Now you can see. And you can look at how dark the texture is. It still works. Huh? So what is great about this is because since I'm building a blend shape model, I can simply use the blending weights and retarget it to an arbitrary character. For example, a dog. So it can do a lot of things, right? It can also like track eyes. Well, now it's a little bit dark. Maybe like this. Does it work?
Yeah, not the light. Can you get the light there?
That's okay. And if someone is wearing some shades, it would probably also work. I didn't try that. Yeah, I mean, it works, right? So it's very robust. Maybe just for some fun, I can show you some completely different characters in org. All right, so that's, what's that?
That demo was very compelling when we did it with Shri the other day.
Yeah. I wish I had 5 minutes more, then I'll do it with you. All right, so that's the live demo. So now I have a little bit of time, and what I'd like to do right now is show you a glimpse of my other projects. I'm not only interested in human performance capture. All these like foundations carry over to many other problems. One thing I'm interested in is, we're doing faces, but without hair, faces look a little bit boring. Is to how to reconstruct hair. So that's actually a new thing that we're looking at. There's a collaboration with Princeton. This is sort of like the acquisition setup that we have. 4 cameras. We're trying to look at different orientation fields of the hair from different positions and have a new way of doing stereo optimization. So we do look at everything in Markov random field, try to extract what the most optimal surface is, and fit strands on it. So this is sort of like the reconstruction we have. So we can capture hair, dynamic hair. That's recently accepted at CVPR. Another project is one with Rob Wang from MIT and 3 Gear Systems. The idea is to do hand tracking, right? Hand is a very important subject to track. So the idea here is to do CAT assembly, to do it in a more automatic way. So I'm always interested in using depth acquisition systems. So here we're putting like 2 connects on top, have a data-driven approach using hands, and try to do gesture recognition in real time. One of the problems here still that we're still looking at is like if the hand has different shapes, it doesn't work as well. So we want to have an on-the-way way of improving the shape of the database. Here's a live demonstration of how things work. It's just like grabbing different things together. Actually, it looks very impressive, but it's a little bit hard to figure out depth, especially when you're looking at 2D. So it's a little bit odd. Here's another project, which is about urban reconstruction. This is recently accepted at Eurographics. The question is, if we take pictures of a different building, this is in New York, and have a lot of reflections, mirrors. This is in my apartment, my little coffee table. You have a lot of reflections. Very hard to solve stereo correspondence. So we want to use high-level priors, geometric priors, to solve for this. Here, lines, planes, symmetry are used to reconstruct these really fine models. Another thing is, what about we just throw away all our priors and everything? What is the best we can achieve without priors? So this is one thing that is accepted this year at SIGGRAPH. How do we fill in holes and obtain a more complete geometry? This is what you get if you look at closely. You see that there is no point-to-point, frame-to-frame correspondences, but luckily I had another submission at SIGGRAPH that actually solves this. We have a one-to-one correspondence where topology is changing, right? The topology is changing of that geometry, and we have a new mesh data structure that can actually capture these topological changes. And I'm very happy that this also is accepted at SIGGRAPH this year. And what we can do with this is, in addition to human performance capture, we can use it for fluids. That's pretty cool. Because fluids, very often, they are level set methods. And you have like you don't have frame-to-frame correspondences, but what artists often want is to have a way to texture these fluids. So if we can texture these fluids, we can have tracking on topology changing subjects. What can we use that for? For example, enhancing a pre-simulated simulation that takes very long. We can add in, for example, like high frequency details, additional wave function that depend on the topology. These are tricks that we can do with that. Another ongoing project with Michael Black is basically how do we understand building a better way, a better human computational model. So we're doing lots of like regression analysis to study the correlation between shape component poses, basically skeletons, with skin deformation and identity of humans. And my research also carries over, as Eitan said before, to other sciences. And I would like to show you two examples before I finish my talk. The first one is in radiation oncology. So this is a really cool project. It's a collaboration with a company called Sirat, part of Electa. And the idea here is to do, it's basically they build a system that has a structured light projection and can track the human body of a patient that is undergoing radiation therapy. In radiation therapy, what do you want? You want to locate where the tumor is. But you can't, you have limited dosage that you can use. The person is getting skinnier and skinnier, and it's like, even during radiation, it's awake, so we have, it's breathing. So what you want is a real-time way to track that person. So what they do is they track the surface of that body and do a, volumetric finite element simulation real-time. And another direction that I'm going is in cardiology. Cardiology, people are interested in why does the heart sometimes fail. How does it react to pacemakers? How does it react to different drugs? There are two ways of doing that. Electrophysiology, and the other one is cardiac surface mechanics. And the more accurate way is to do electrophysiology, which means looking at how does the electricity moves on the surface of the heart. But the problem is they need to arrest the heart in order to measure that. How about we can do it while the heart is beating? So that would be more accurate, but there's no way so far to do that. And from a geometric perspective, this is a simple parametrization problem. So what they did here is a little bit crazy. They took a rabbit, so it's on animals, not on humans. Took a rabbit, opened up the chest, and took out the heart while it's beating. And built this mini structural light system that you've seen before. Captures at 667 hertz and 200,000, and 200 points at the size of a walnut. So on the left, this is the input acquisition, and on the right, this is the tracking that I could have, I was computing. So essentially, we need to evaluate how accurate it really was. So we have a heart, we took a nose spray, put some ink on it, and manually tracked it by hand. And so our measurements on a markerless system is sub-millimeter accurate. So it's very accurate, and it doesn't drift over time. What people can do from that is they can extract displacement energies, curvature, strain, stress, all the things that biomechanics people are very interested in. So this has the broad application. And so this is one thing that's currently under review at Nature. And the other project is on the radiation oncology. It's being deployed in 50 hospitals already, so it's FDA approved. So it's kind of cool that it works in other sciences. So here's the vision. Here's a little bit about why I believe this whole thing will have a future. Here's like a little video from a lot of you might have seen that before. So it's like a future concept of what Microsoft is predicting. So it's a little bit of a science fiction thing. You know, you can have like air instruments. So basically, natural user interfaces. The way human will interact with electronic devices will change. It can improve our lifestyles. Here's a very hot topic as well, virtual try-on systems. These improving our everyday life. And another thing is, of course, security, biometric system. If we walk into a door, we want to be able to recognize that person in real time, but in different scenarios, even when the person is changing its expressions, mood, clothing, etc. I believe that these things carry over to mobile devices. So having depth sensors that are more reliable, works in the dark, different illumination conditions on mobile devices, that might be the future. And one last thing is, this is where we are today, right? So this is like what industry standard is. They're able to capture all these joints. It's not very accurate. It's not very high res of what you can get out of a system like Kinect, but it's going to drastically change. One new sensor technology is actually coming, and this is a spin-off from NASA, which is very interesting. Was originally used to analyze crystals, and it basically is a passive camera system that can see depth under any kind of conditions, which is very strange. So, I mean, the results are unbelievable. And also the amount of details that people can capture is also like incredible. So I know that like there's some people trying to understand how this works. So this thing is currently only for government use, and but it's very promising. So someday these kind of technologies will come out. Here's another examples. You know, you have some slight transparent surfaces, and I mean it's very, very good. So you know, you have new sensor technologies that will come, that will be soon available. So my research agenda is the following. You know, in computer vision, we're interested in telling a story out of a picture. I'd like to do the same using geometry, dynamic geometry that are being captured. So the question is, given that, what can we tell? What can we tell out of it? So I want to achieve this with the three following steps. The first step is, I want to build more sophisticated rigs, more sophisticated models, computational models of humans, you know, with hands, faces, and bodies, everything in a unified system. And it would be great to have a systematic approach to solve this. The second thing is on-the-fly treatment of these dynamic data. So we need to explore what are, you know, dimension-reduced methods, regression analysis method, to have a very compact representation of what these dynamics and all these poses are. Both of these things are tightly linked together, so each of them will improve each other. So these are like parallel directions. And ultimately, what I'd like to do is what I call the digital mind. What is the intention of a person doing something? Just by looking at the geometry, just by looking at the models that we have fitted onto these captured data. And these things, obviously, as you've seen before, has a huge line of applications, from entertainment, security, to lifestyle improvement, social media, etc. And I would like to end my talk by thanking the following people. The principal investigators, Ethan Ritzput, Simon, and my PhD advisor, Mark Pauli. And of course, I'd like to thank my wonderful collaborators and my excellent students, very talented students, and the funding agency and the industry collaborators. Thank you very much.
So we're a little short on time, but we're going to take a couple of questions. Al?
Can you do automatic lip reading?
Not yet, but this is something that people, for example, in graphics, when they see that, the timing is very good, but lip is very difficult because it has a lot of occlusions, right? So the way to solve this is to, have a more sophisticated rig that would recognize what the person is doing and then to synthetically generate from that.
Peter?
On your demo,
Yeah.
You had some initial blend shapes.
Mhm.
How do you determine what those are?
It's very difficult. It's a trial basis. So,
So if you used a different set of those, you get a different result.
oh, you mean the training expressions? Yeah, absolutely. And it doesn't work well on everyone. But some people, also some people can make all these expressions. So it performs differently on different
Have you
people.
thought about how many blend shapes you actually need? Because he was talking about, Etan was talking about thousands. You had like 5 or 6.
Yeah, actually, this is one important research question that we need to look at in the future. If you have, at the current point, if you have too many blend shapes, it also doesn't work. So it's very difficult to solve for small blend shapes, and it's just ambiguous, and you might get into some wrong local minimas in that case. Yeah.
John and then Steve.
In Toy Story, there were critters with 3 eyes.
Yeah.
Monsters Inc., there was a critter with 1 eye.
Yeah.
Shrek doesn't have any ears.
Yeah.
What does your system do?
It can work. So basically, so I didn't show this, but in order to do this, what you need to do is to have, let's say you have the 1-eye monster, and I close my both eyes. I have that rig, and I have to explicitly specify the correspondence between these 2 shapes, and then I can map from my expression to this. I don't need to specify one-to-one correspondences between, so I don't need the full blend shape of the target. One way to solve this is using support vector machines or vector analysis to get the mapping between 2 different, it's an established thing that people do this all the time.
With regard to the animation prior work, if you have a performance that has a lot of rapid transitions between expressions, wouldn't that bias you unfairly towards the earlier expression?
Yeah, the animation is smoother. But what we found out what was important is that you really don't get wrong things. Because if you have wrong things, it just doesn't appeal for actual use. Right.
But you could clean that up later, right? If you knew
Absolutely, yeah.
follow.
Yeah, but correct, yeah. You could clean it up later, but not for real-time use. Right. So we really, the thing is, if we turn that off, you really get some really strange faces, and the purpose was really to avoid those to happen. But you're right. I mean, it will appear
But if you put it on
smooth.
that, you could then take the ones that occurred after that point.
Oh yes, right.
Etienne?
Oh,
All right. No questions? So, Augustin?
I just want to say that do you have a metric to estimate your exclusivity? Because one way
What trick?
Since many of your applications are to art, do you have a metric to
A metric.
yeah, just a measurement to know if your system is exclusive enough or if you are basically too neutral in the choice of your face.
Sorry, I didn't hear the last part. A metric that is for what?
That allows to know if the face is too neutral or too expressive.
Yeah, you can do that. I mean, basically, you have. Basically, it's straightforward. Every blend shape will be determined by its coefficient, by its amount. So that can be one way. This is like the most straightforward way of measuring how far away you're from the neutral pose. What is actually very interesting is more of how can I build a generic model and map it to an arbitrary face. So that's actually what I was talking about, the on-the-fly research focus that I want to do in a couple of years. Is like, how can you avoid this construction part, right? So you need to factor out identity and expression at the same time. So this is more difficult, right?
All right.